So yeah, welcome everyone to the sixth talk or the seventh talk of the Equivariant Elliptic Cohomology Seminar. Today we have Niklas Kipp from University of Regensburg, and Nick's gonna tell us about construction of equivariant elliptic cohomology theories. So Nick, please take it away.
Yeah, thanks. So hopefully everybody can hear me. Feel free to interrupt any second. So I don't see the chat or anything. So just, I don't know, let me know. Yeah, so I guess, I'm supposed to explain or give some idea how to construct this equivariant elliptic cohomology. So maybe let me, I guess, recall elliptic cohomology. Yeah, I hope my handwriting is not too horrible. Let me know if you can't read something. So I guess, there's probably, it's a difficult theorem, but one can maybe summarize it in the following way. There exists some, I guess, spectral Didi-Mumford stack together with some, I guess, sheaf of function, which is, for example, you can denote like this, so like E infinity rings, such that if I forget to just, like, I guess, homotopy commutative algebras in spectra, then like this composition comes from the Landweber exact functor theorem. So I guess, I think we've discussed this. So what this means, or one thing what this means is that it, in particular, is that if I take, if I take an Étale point in this moduli of elliptic curves, this corresponds to some elliptic curve. And if I look at the completion at the unit, then this is given by the following formal scheme. So I guess I can look at the functions of R and somehow ask what the cohomology of CP infinity is. Yeah, so I guess, I think we've discussed this a bit, and somehow now I guess the question now is, how should we define equivariant versions of these elliptic cohomology theories? Okay. Right. And I guess, we'll try to explain an answer for this. So maybe maybe the main motivation, or one motivation for this, which we probably also, which we also have discussed, I think, is that, right, somehow, like this Landweber exact functor theorem here, whenever I take a formal group, then this, so out of using this Landweber exact functor theorem, one can out of formal groups, one can produce cohomology series. So one example of such a formal group is if I take GM and complete it at the unit, and then this Landweber exact functor theorem, we get some, I guess, this is even an E infinity ring, but then we get this homotopy commutative ring in spectra, which is often called, I guess, complex K theory. Also often denoted KU, whatever. And so now the cool thing here is that, I mean, this has a very natural definition in terms, I mean, in equivariant situations. So this natural version. So now G, no, this looks horrible. Right. So that's K-theory of G equivariant vector bundles. So, right, I mean, like, for example, I can define the K-theory of a ring as like the group completion of the groupoid of projective modules. And I can just look at the groupoid of equivariant, I mean, like, projective G representations. And then I guess this should be a way to define this equivariant K-theory. And then one can also produce a map from like this equivariant thing of the point to the K-theory of BG. And then, yeah, I guess the reason I'm saying this is then somehow, if I can, also there's this general Sega completion theorem. And like in this case, I want to apply it for S1. Then then that this map, I mean, like I can look at this map I've written down here, and this is actually isomorphic to something, I guess, familiar. So I would like actually to speak of geometric objects. So CP infinity. Then I mean, like this a map above gives me a map like this. Point. And I mean, one can compute that this corresponds to GM, and this on the left here corresponds to the completion at the unit, and this is actually exactly the map. So completion at right. So I mean, this somehow, I guess the reason I'm saying this now is that, so the idea would now be that whatever an equivariant version of our cohomology theory is, we should be able to recover or rather it should be the ring of functions on our elliptic curve, right? Idea like for so if I take an elliptic curve, then I can look at this map where complete at the unit, and I mean on this side we should have this with of CP infinity, and on the other side we should just something like, I mean, so I mean this is, so yeah, this is somehow not really true, because I guess, I mean, yeah, I guess in general an elliptic curve is not affine. So I mean, yeah, so I cannot recover the elliptic curve out of its functions, but somehow this elliptic curve is more general. So this maybe let me write this in like quotation marks or whatever, just explaining an idea. And I guess the point I want to make in this talk is somehow that this idea dictates everything for us. So this dictates us where to go. this tells us yeah. So does this make sense so far? Are there questions? Okay. Right. So I guess first I want to make a little digression, I think, and sort of say a few words about where this map here comes from, or where, I mean, how are we supposed to understand this map in, yeah. So digression on pre-orientations and Quillen formal group. Yeah, I'm really sorry. I feel like my handwriting is horrible, but yeah, at least you see close. Yeah. Okay, so I recall if we have like some complex periodic infinity ring, let's say A, then yeah, we can produce a formal group by looking at the cohomology of CP infinity. So and I guess this formal group is somehow what I want to call the Quillen formal group. And yeah, I guess so. What I want to, I mean, partly I want to like give a more concise or more concrete definition of this guy and explain why, yeah, in some sense this is like the free formal group on S2, I guess. So like this, the following proposition. So if I have some formal group over R, where R is complex periodic, then the space of pre-orientations of this formal group, which is, I guess, defined to be, I guess, the mapping space in pointed anima from like S2 to, so I guess by definition, this is actually an invariant on like connective infinity rings. So we just force it to be connective. And then the claim is that this is canonically isomorphic to the mapping space in formal groups over R from this Quillen formal group over R to our formal group. Right, and I mean this, right, so this, so I mean this is somehow why we I guess I can, of course, so at least any pre-orientation will give me a map of this kind, and then to ask that I actually get that this actually corresponds to the complete, oh wait, this is not actually true. So I guess what I wanted to say is somehow I start with my I guess formal group in this case, or in our case, I think we wanted to start with an elliptic curve, and then we can complete it. And I mean, one step in saying that, I guess the completion is of this form then is that we want to produce a map of this kind. And then, yeah, I guess in the paper we're discussing the definition of an orientation is then just asking that this induced map is an isomorphism. So then this way we obtain this map here we would like to have. Yeah, so I wanted to say a few words about the proof. Right, so I mean, I guess formal groups are certain group objects in certain, I mean, yeah, informal schemes, I guess, or at least certain. So I guess these in particular have the form. So we want to look at. So I guess if we want Tn, right? So we look at affine spaces completed at the zero section with continuous maps, right? So now a formal group is, I mean, a one dimension. I mean, one of these guys, but in dimension one and has a group structure as a scheme. So what I want to do now is like give a different description of these. And the claim is somehow that there's a, right, by taking the R dual, one can identify this with R coalgebras, which locally, by locally, by the way, I mean Zariski locally, of course, of the form. Yeah, they look like the divided power coalgebra on just a finitely generated free module. Divided. Note that on the left-hand side, we don't assume any continuity anymore. So we don't really have to take care of some tricky limit, for example, which makes this, I mean, this perspective kind of convenient, I guess, for example. So let's give these guys a name. We'll call them smooth coalgebras. It's not me who gave this name to them. Yeah, so I guess now, because, I mean, I hope this equivalence makes it believable that one has a fully faithful functor. So we can look somehow as there's some spec construction for these coalgebras over R. And this is fully faithful in like functors, connective. I mean, like E infinity rings to Ani. And maybe let me write a formula. So this co-spec construction of some Z applied to some A is just given by the following mapping space. So I can look at the maps in commutative coalgebras from A. I mean, this is a coalgebra over itself. And if I tensor C up to A, then this is, of course, a coalgebra over A. Because, I mean, yeah. Right. So I have this construction, which is fully faithful. And I guess, so now, yeah, so I guess actually the concrete definition of like a formal group in I guess elliptic 2 is then that I can just, yeah, I can ask for I mean things which live in the image of this functor, somehow have dimension 1 and form a group book object in appropriate sense, in the sense that like this, I mean, this, yeah, I guess I guess it takes values in connective abelian groups. That's one way to say it. Yeah. So maybe an example. So if R is complex periodic, then I can look at the homology of CP infinity with coefficients in R. And then this is a smooth coalgebra. Is smooth co. I mean, yeah, I guess there's some dual computation to, I guess, some, yeah, to like the classical compute. I mean, right, like the cohomology of such an E infinity ring. I mean, yeah, we'll have this kind of form in dimension 1. So I mean, yeah, it's very, very believable that one can also compute a homology and gets a guy of this form, right? Right, and I mean, yeah, recall also maybe like the I mean, like here, I mean, that's this guy, for example, represents line bundles, and now the tensor product of line bundles gives me some multiplication on this, which gives some group structure. So this is actually, yeah, this actually is now this is what I mean by a more concise or more concrete definition of this Quillen formal group. Okay, and now, I mean, now one can do some computation argument for this proposition. That's right. So this is the co-spec of some C by definition, as I said. And now pre-orientations of this G is, I mean, first, I guess I can somehow use their junction to connect the Fabian groups. Is there, wait, I'm confused. I'm confused. Oh, no, it's fine. Yeah. No, yeah, it's just by junction. Like this. Okay, now let's maybe. So I want to understand this as an abelian group object. Maybe, right. This looks more familiar to you, or like, I mean, I could also write the second Eilenberg-MacLean space if you want. And now I just, I mean, write out what the R values of this formal group are. Now I can use, I guess like yeah, I guess just the, yeah. I mean, here implicit, I just use somehow that like the category of co-algebras has, I guess, co-limits, and so I mean I have a canonical action of anima on this category, which I mean gives me some adjunction, and this adjunction one can check gives me an adjunction in abelian group objects. So this is by adjunction also the same as just like the homology. See, and now we are exactly, I mean, now both of these guys are actually smooth co-algebras. So I mean, what we have written here is another way to say what like I guess formal groups are, right? So this is just the same as groups over R from query-informal group. My sketch of the proposition here. Yeah. So this, I mean, I'm not sure if this was discussed somehow. This is right. I mean, this is really the starting point idea, and then, I mean, this notion of an orientation somehow comes from the question: how do we actually, yeah, if we have our elliptic curve, I mean, how do we understand the completion as such a gadget? Are there questions? Maybe I'll stay at the proposition. Right. Okay. So now I guess this was the digression. So now I want to somehow go towards the construction of equivariant elliptic cohomology. Yeah. Okay. So I guess let's give us an elliptic curve. Let's back over R. And I mean, let's maybe take some anima together with some action of S1. And let's maybe simplify notations. Write A for like somehow the cohomology, the E infinity ring associated. To R, coming, I mean, this is like this, yeah. There's still this structure sheaf we have on this. I guess, as I will mention later, actually the Deligne-Mumford stack, which represents oriented elliptic curves. Right. So I guess the first thing one maybe observes is that, right, so like this, if I, whatever this gadget here is, oh, sorry. So if I evaluate whatever we want to have on, I mean, the S1 equivariant elliptic cohomology of X should definitely be an algebra over this gadget applied to the point. But remember that this actually should be the I mean the global sections of or the functions on our fixed elliptic curve E. So I guess this should be then the functions of some coherent sheaf on E, right? Somehow the idea. So that's one X. The functions on some F. I guess, I mean, I prefer this notation, but I guess in the paper they more write Q of E. So there should be some quasi-coherent sheaf on this elliptic curve, such that, I mean, if I take global sections, I recover this ring here. And I mean, right, this directly, I mean, somehow then one can directly also ask for a same situation if I fix any other G than S1, right? Like more. Generally, one can ask for, say, G is, I guess, it's a bit of a spoiler, but a compact Lie group, so does there exist? And now I also already spoiled this because we had the notation already. Or maybe exist a geometric object, which I will denote by this. Such that, like, if I take some anima, say with G action, AGX comes as functions of some coherent sheaf on this geometric object. I think I'm going to take this. And right, so then I guess here to make this more trackable or more concrete, I guess like a very nice idea I find is the following. So at least for compact abelian Lie groups, one can somehow use Pontryagin duality to get something nice. Duality. Like, my horrible handwriting is very convenient when it comes to me writing words in a wrong manner. Duality. Right, so I guess we even had, like, I mean, the actual version we will use then is some version for BGs of compact Lie groups, abelian compact Lie groups. But I mean, the classical statement is just that I have compact. I mean, one way to say this, I guess, is that there's an auto equivalence. I mean, like some equivalence which like flips the arrows from compact abelian Lie groups or compact abelian groups to abelian groups by looking at maps into S1. Right. So, and now what one can do is the following construction. So for a compact abelian Lie group, I can produce this LBT, which I mean should be a geometric object, which for us means that this is like a functor from connective infinity rings to anima, and the assignment sends such an R algebra to the following Hom set. So I can look at, or maybe I wrote mapping. Okay. Maps in connective abelian groups. And then I take the Pontryagin dual of T, which is, I mean, a abelian group. And it's, I mean, by definition, this our elliptic curve takes values in connective derived abelian groups. So I can look at this mapping space. This is And I guess this will be our geometric object you would like to consider. I'm not sure, I mean, yeah, I guess this was said, at least orally in the seminar, but I mean, like this is also the same as the being group objects in Oni. Right. Just to, I think this was the notation for being group objects. Or like, I mean, I guess I can like P sigma of like 3 finally generated Abelian groups, which is also, I guess, the animation of Abelian groups, for example. It has endless names, I guess. Right. So, okay, this is the geometric objects, and now to, I mean, yeah. So now I guess the question is, like, in what sense is this construction functorial? Right. Yeah. So, what is the functoriality of this L thing? I mean, due to the fact that this was actually concretely constructed already in the seminar, I will not give the actual construction, but try to like more explain where the construction comes from. Yeah. So I guess the first observation is somehow that, yeah. By the way, if anything is unclear and you don't want to ask a question, or I'm not able to answer a question, everything I mean, essentially just learned this by reading this survey of Lurie. So there's nothing crazy. Everything probably there's nothing I add to this survey. Okay, so I guess the first observation is somehow that, like, note that if I look at this gadget of a point, then this somehow does not depend on G, but rather on BG, right? This should depend just in the sense that it does not depend on the base point of G or the unit. So I guess, right. So I mean, somehow we want to, like, the domain of our cohomology or of this functor somehow should be given by the category of these kind of objects. And I mean, this we have discussed. So I mean, this is denoted, I think, like this, probably called orbit spaces, if I'm not mistaken. Should be the domain. Okay, so that's probably not surprising. And then I guess maybe the more crucial thing is that, like, these pre-orientations in a way determine what we want to do on mapping spaces. So in the following sense. So one can, I guess, like, if I look at this mapping space from some BT to BT prime, both are, I guess, now abelian compact Lie groups. Then one can compute this as this following product. I don't know. And right, where this side somehow depends, I mean, corresponds to choosing some, I mean, fixing some base point, and then I guess this probably we have even discussed this in the very beginning of the seminar. This appears also in the first, probably second chapter of the paper, in some sense at least. And I mean, here, it's relatively clear what to do, right? I mean, this construction, of course, is like functorial in T, right? So I mean, like on this is, yeah. So maybe I write clear this side. So what would be the correct? So the question then boils down: what is the correct map from BT prime to maps from L BT to L prime? And I mean, because any T has a map to the point, I mean, one could, for example, just factor this map. Yeah, to, I guess, right. So, I mean, to this mapping space, but now I look from, I mean, I put in the point here, and now if you carefully compute, what you get is the following. Maybe don't need to be too careful. Then you will see that this is just this mapping space. And right, so, and now this left side, this on the left, one can also see, maybe if one is a bit more careful, that this one can compute as P infinity, right? But here, I mean, here we have a clear idea what the map could be, right? So I could just post-compose with my pre-orientation. And yeah. Okay, so we sort of have an idea what we want to do in mapping spaces, and maybe to, yeah, so yeah, maybe to the correct target we get by if we don't take like if we don't fix a particular elliptic curve, but maybe a good idea would be, where are we? Right, so maybe we should, yeah, I guess a good idea would be to just take the universal one. So maybe for this we had this, like if we look at, I mean, this is the classical, I mean, the underlying, I guess if you want, this is the underlying topological space of the classical moduli of elliptic curves. Okay, topological étale site is what I mean by topological space. And there we have some structure sheaf. And so this data together is, I mean, is maybe spectral the Mumford stack. I mean, not maybe, it's definitely spectral. Which I guess will denote like this, such that like the R points for some infinity ring is given by oriented elliptic curves. Oriented over R. In particular, I mean, there exists a universal oriented, I mean, as some, I don't know, maybe as some étale sheaf or whatever, there definitely exists some universal oriented elliptic curve. So should So right, so E unif, which now lives over this moduli as a target. Or maybe, I don't know, to produce a target. Right, by this I mean that, I want, or we want, or everybody wants a functor from like this orbit spaces to the entire side of this moduli of oriented elliptic curves. And the concrete construction was, I guess, yeah, combinedly given in the last two talks at least. So this, yeah. Okay, maybe something I did not. So this, exists. Maybe something I want, maybe something orally. So I guess somehow I have sort of discussed what to do for abelian compact Lie groups, and to go from abelian compact Lie groups to all compact Lie groups. At least what happens in the paper is just that they can't extend. So they just use a left-Kahn extension to go to all compact Lie groups. And yeah, not particularly familiar with equivariant homotopy theory, but I was told that this is like a general philosophy. So for example, this holds also for the K-theoretic situation. So probably is a good idea. Right. Are there questions about this motivation? Or like, anything else also, of course. Okay. Okay, so then, yeah. Let me define equivariant elliptic homology. So this is the following construction. Let's fix some compact Lie group. Then I guess one can prove, or one can define this category probably of G orbits as like a full subcategory of wait, this is not just, yeah, no, I'm confused. Please correct me if I do nonsense, but I would have guessed that this is this sliced over BG. And now this, this should be the full subcategory of objects which come from injections H to G, like, subgroups. And then, one can produce some functor, which is now, has this curly L, this notation from op G to coherent sheaves on this L BG, and it's contravariant. And since such a BHF mapping to BG to this map F, this induces me a map on stacks after I've applied L, and then I can just take the push forward of the structure sheaf. So this is F lower star of O L BH. And I mean to then this category of G spaces is just the co-completion of this category. So I just take just pre-sheaves if you want on this category. So I can just extend by co-limits to get a functor like this. Right. That's then the left Kahn extension if you want. Which also will be done by G. And maybe if you're irritated because you're looking at the paper at the moment, like if for n, wait, but I just look at injections. Oh, this MS. Okay, so maybe a remark is like for an injection, or like of a subgroup. Actually, this map L BH to L BG is affine. And so the reason I'm making this remark is that, right, so I could here, this is a subcategory of just the étale sheaves of this on this L thing. And somehow computing this global sections functors on the sheaf side is, I guess, easier. So it's always nice if you have the situation that you can compute, that this lower star automatically will land in this category of coherent sheaves. And this is the case for affine morphisms, for example. Because this both categories are some limit of categories, and because the map is affine, you can just like this lower shriek is really induced of a as a limit of scalar restrictions on just categories of modules on rings. Right. So I guess in the paper they often this has some adjoint disinclusion, and which they write as Q. I guess it goes here. And then they in their formulas often this Q also appears. But yeah. So just a different lower star if it doesn't coincide. This is not confusing. Okay, so now right. So now I want to maybe this Kahn extension procedure here looks a bit brutal, or yeah. But so I want to explain why this gives the correct answer. So somehow proposition, or so if I take some x in G spaces, then of course I get a map from L x G to L, just induced by the map from x to the point. G. And a different way to say what now what I guess this elliptic cohomology of the functions on this coherent sheaf of elliptic cohomology on an axis is I could also just like push forward the structure sheaf on this stack to here, and yeah, I guess the statement is that this is the same thing as we have just constructed. So there's no ambiguity somehow. And let me say orally again, we run into this issue that, I mean, this lower star might be difficult to compute. But for example, if x is finite, then one can show that this is, I mean, this lower star on the level of sheaves again is actually quasi-coherent. So then it becomes easier to compute. Yeah, I'm not. Right. Right, so let me explain the proof. Like, what do we have to check? I mean, right, this is definitely, I mean, by definition, we have the same construction on the representables here in this G orbits. So if we show that this construction here preserves colimits, then we're done, right? Because, I mean, this preserves colimits and they coincide on representables. So let me write this. We want to check that this functor here to, I guess, now I can, yeah, so now I can I mean, maybe first set, let me write set as in the paper, BG, just to shorten notation. So right, I mean, actually we want to check that this functor to coherent sheaves preserves colimits. But yeah, I guess, I mean, the inclusion, I mean, the inclusion of like OX modules into of coherent sheaves into this modules over the structure sheaf of Z preserves limits. So if we put this up here, then this will become colimits. So right, so we can just, I mean, and of course, I mean, that's even fully faithful. So in particular, this is conservative. So we can just ask if this composition to modules over the structure sheaf in étale sheaves preserves colimits. Right, and now this one can factor in the following way. So this is S orb sliced over BG. And now we can go to just sheaves on Z. Op. Right, I mean, this is this L functor, but sliced. So preserves colimits. And I mean, this functor comes from this inclusion, I guess, we had earlier, and preserves colimits as well. This might be, yeah, I guess this was also maybe discussed in the beginning of the seminar. So this composition here preserves colimits. So we just have to check that this functor here preserves colimits. And I mean, yeah, probably hard because I didn't tell you what the functor is, but it's a functor which makes this diachrome commute, of course, and I will maybe tell you what the underlying space is, and then you can guess what the functor actually is. So I can look at omega, and I mean, yeah, I can look at the underlying space, and now compose this. I mean, then the composition will be, will be the functor which sends something living, something living over Z to, I guess, H lower star or Y. And I guess this is probably right? And I mean, right. So now this functor here is just this guy. So like such a slice goes to this sheaf, and I mean, something one has to observe now here is that this functor here preserves colimits. Note that we have ops everywhere, and also is conservative. And I hope, yeah, and yeah. So here, I mean, this conservativity is, I mean, if everything was connective, then this is clear, but we are not connective. But locally, we are periodic. So, I mean, also the negative homotopy groups, I mean, at least locally, I can also recover the negative homotopy groups if I just have the positive ones. So, yeah, we use something in this claim here, namely that this stacks here are local. I mean, locally, the ring of functions is an even periodic or two periodic infinity ring. Something to, I mean, for conservativity, we can check this local, and locally we have this. Okay, but now, so what I want to say now with this is somehow to check that this preserves colimits, it suffices to check this preserves colimits. And yeah, so this means we need to argue for this. But this now follows by just writing out what we have here. So if we look at this, at the value at some u over z, then this is given by the following mapping space, the mapping space over u. And I mean, like these sheaves of functions as like an ordinary algebraic geometry are represented by the affine line, right? I mean, these are really functions in some sense, not in some sense, they are really functions. And this A1 here means, I mean, to make this true, of course, I take the free infinity ring on bond generator. It's a bit complicated what this thing is, I think, but yeah. We just need actually the representability, because it's clear from this formula that this, I mean, preserves limits in y, right? Right, but I mean, like limits, I guess limits in this sheaf thing are just computed pointwise. So this explains why this composition here preserves colimits. And then we're done. Are there questions about this? Yeah, so I'm not exactly sure how long I have. So I think I have another proposition which I would maybe at least state, and then you can let me know if I should also say what about the proof. Right. So okay, maybe I mean, I purposely somehow chose to stay in this concrete example of the universal elliptic curve, but of course, I mean, one can somehow axiomatize the situation and work with, I mean, arbitrary spectral Deligne-Mumford stacks, where together with some elliptic curve over them, and yeah, I guess like somehow now in this last proposition we use that locally like the structure sheaf is supposed to be two periodic. So note could be any locally two periodic Deligne-Mumford stack together an elliptic curve of it. maybe pre-oriented, sorry. And pre-oriented. Right, I also forgot to say this in the beginning. Whenever I say spectral, I mean, I guess we call this in the seminar derived. It's just, I mean, I think of something different, to be honest, if I think of derived. Like locally, everything is screwed off out of infinity rings. Okay, so now, I mean, right, so now one can, like one last thing I want to discuss is somehow what one can say if we like let these Deligne-Mumford stacks together with the elliptic curve vary. So one can say the following. Proposition is, so I have the following situation. I have some Deligne-Mumford stack M and something N, and a map between them, and then I have some elliptic curve over them. And I guess the pullback here will give me another elliptic curve. So I have this Cartesian square, where these are, I mean, these kind of Deligne-Mumford stacks, too periodic. Even though I'm not, probably one doesn't need this for this proposition actually. And these are pre-oriented elliptic curves. Right, I mean, everything I discussed somehow makes, I mean, there's an obvious generalization to like an arbitrary, I guess like a pre-orientation, for example, definitely makes sense in an arbitrary topos. Like an elliptic, I guess also. Okay, so the statement is, first of all, if I now take the pullback of L, I mean, take this composition of functors, then this is also the same as this L construction for this pullback of the elliptic curve. And I guess the second statement is that if I look at this curly L construction and pull it back, then this is the same as L applied to star E, G, as functors from, I guess, finite G spaces up to coherent sheaves on star L, E, and this is probably a BG. And now they write in the paper for G a compact abelian Lie group, but to be honest, I don't really see why they need abelian. So let me write like this. For compact abelian G. Maybe somebody sees why abelian, but yeah. Let's see. Okay, so yeah, I don't know. It's okay if I also say a word about the proof and then finish, or should we just?
Yeah, maybe you can talk about the proof.
Okay. I mean, probably it's not more than 5 minutes. So what I want to say about A is very easy. So for A is just unbind the definitions. Unbind the definitions. And then you can see this. And for B, I mean, right, so if I take look at both sides, then I mean, right, so I mean, maybe something to note here is that this upper star here comes from a map, I mean, from a left adjoint of like a geometric morphism of topoi. So what I want to say with this abstract nonsense is just that this, I mean, this preserves co-limits, but also finite limits. And for that reason, this left-hand side also preserves finite limits in total. And this, I mean, this even preserves all limits, I guess, if we would be bigger here on the domain. then, yeah, so, right. And now, because both sides preserve finite limits, we can, because this is somehow why we chose this particular domain here, we can reduce just to the case of a representable again. Right. So both sides preserve finite limits. So suffices to provide, I mean, for some subgroup yeah, I guess functorial equivalences like this. Okay, this is not a Y, this is supposed to be a G. From like G mod H to F upper star of E, G mod H. Right, but this, I mean, this is really a base change formula if one observes the following. So, but this follows from base change following square. So I can look at this L construction of like EH, and I mean this admits a map from L E G, and coming from the inclusion, of course. And now I can, right, so now the I also have a map from like this pullback of E like BG. And then one can observe that, I guess this also uses the first part, that this pullback here is given by H. So I have this following Cartesian square. And I mean, any such Cartesian square, because I mean, we just work in the derived setting everywhere, gives me a pullback, a base change formula on the level of coherent sheaves. And then I just look what this tells me for the structure sheaf and get this formula here. Yeah, I think this is all I wanted to say. Are there questions?
So maybe let's thank our speaker first. And yeah, then we are open to questions. All right, if there are no more questions, let's thank our speaker again, and then I'll stop the recording in case anyone has post-recording questions.